Let's start. Welcome everybody to the digital communication lecture, which is the fourth lecture called Digital Multiplexers. In today's lecture, we will be talking about the different types of digital multiplexers. Basically, after you sample your signal, you want to what would be the sampling rate or the data rate of one line per user? It would be like maybe 64 kilobit per second. In this case, you don't have only one user, you have multiple users, and you need to send them over a line. You need to multiplex them with other users using time division multiplexing. So this process, of course, you don't have only 24 users, and your network needs to collect the data coming from thousands of users. So there are cables that can support up to 1 megabit per second. How many users this cable can carry? You need to know as an engineer, as a digital communication engineer. There are cables that can support 100 megabit per second. How many users can be uploaded on this cable or served? So this we call it digital hierarchy. We will be talking about it in this lecture. And hopefully if you have any questions, any concerns, any not clear things, you can ask me, interrupt me anytime. But basically, we want to understand this very deeply, and so that we can be able to calculate the amount of data rate that each line can support, or if I give you a certain number of users, you can say whether this link can support them or not. In TDM is for time division multiplexing. A group of analog signals are sampled, yes, sequentially in time. At a common sampling rate, we call it the multiplexing sampling rate, and then multiplexed for transmission over a common line. Is that true? This is what we explained in the previous lecture. In this section, the multiplexing of digital signals at different rates will be considered. This is the purpose of this presentation. Multiplexing of digital signals at different rates. Multiplexing of digital signal is accomplished by using a bit-by-bit interleaving. 1 bit from the first user, second bit from the second user, because you have BCM signal now. You don't have pulse amplitude modulation signal. You have digital communication, you have bits, and you want to multiplex them on the transmission line. So you get 1 bit from the first, second, third, fourth. Not necessarily 1. You can take, for example, 4 by 4. 3 by 3, but this will delay, for example, the reception of the data at some users. So to avoid this latency, we usually serve them sequentially 1 bit by 1 bit. A selector switch, which is the multiplexing switch usually, takes sequentially a bit from each incoming line, then applies it to a high-speed common line. For example, the internet cable that's connected with your PC, how much data rate it can support? It can support up to 10 mega, sometimes 100 mega if it is really good. Mega. But when you have 100 users, can this cable support them? It cannot. You need other high-quality cables that can have higher bandwidth so that it can carry the data rate generated by all these users. At the receiving end, on the other side, this is at the transmitter, you take one side. At the receiving end, you do the opposite. You have multiplexing sequence of data bits coming to you. You just take the first bit, and you know the first bit for the first user. The second bit for the second user. Like this, you receive the sequence like this. This sequence represents all the multiplexed user signals. And at the receiver, the first bit, you know, is for the first user. The second bit is for the second user. Third bit for third, and so forth, so on. Because at the transmitter, you were getting 1 bit from the first user and put it on the transmission line. And then from the second user, you take 1 bit and put in the transmission line. From third user and put in the transmission line. The receiver knows this process, he just do the opposite of that. At the receiving end of the system, the output of this command line is separated out into its low-speed individual components and then delivered to their destination. What's low speed? This, we call this line high-speed data rate line, high-speed transmission line. And when you connect it with the users, with the end user, we call this line low transmission, low data rate line. So this carries more data, this carries less data, can support low data rate. So this is basically the process that I was drawing. You have the first user, second, end number of user. You have multiplexer, which is switch taking one bit sequentially. And you have these high transmission lines. And you have the demultiplexer that takes the bits in the transmission line and distribute them on the receiving users. That's basically the basic concept of digital multiplexers. Now, digital multiplexers can be divided and classified into two major groups. The first group is used to take relatively low bitrate data streams originating from computers. Directly takes the data you generated from your computer or from your PC, and multiplex them for TDM transmission over the public switch telephone network. Actually, the network that supports you get the internet from Turk Telecom. Yes, scientifically we call this network public switch telephone network. Of course, it includes ADSL, very high speed ADSL, and all these versions, even include sometimes optics. This group requires the use of modulators and demodulators. Because why? Because it interacts with your network card. Your network card, the pulse amplitude modulator and QAM and all this modulation happens in the network interface card of your computer. That's the physical layer of your motherboard, yes. So the second group forms part of the data transmission service. These multiplexers, since you are in the data link layer, not on the physical layer. Now you don't have signals, you have bits. You multiplex bits. These multiplexers constitute a digital hierarchy that time division multiplexes low rate bit streams into much higher rate bit streams. So one at the physical layer, one at the data link, one multiplex the samples, the other multiplexes the bits. The first type of multiplexers that we will talk about is the basic digital hierarchy. We call it DS0, that takes one voice signal, then samples it at a sampling frequency of 8 kilohertz, and then convert it into BCM using 8-bit quantizer. If it uses 8-bit quantizer, how many levels does the quantizer has? It has 2 to the power 8. 2 to the power 8 is equal to 2, 5, 6 level. 256. Because 2 to the power 9, 512. 2 to the power 8. See how many levels? In the exam, we cannot ask you about this. We can tell you up to 3 bits, 8 levels, so that you can solve it. And this is the question I gave to you in the previous lecture, in the previous course we took together, Introduction to Communication. Because if it becomes like 8 levels, you have 256, you cannot finish. You need a computerized system to finish this. But the most important thing, we teach you the concept, then the complexity and the computational things, the computer can do them much better than us. This means that the DS0 is basically then a PCM signal, a digital signal for one analog message generated from one user. This is what's DS0. What's the data rate produces by DS0? 64 kilobit per second. How did I calculate this? You have the sampling frequency 8 kilohertz, and each sample has 8 bits. So 8 multiplied by 8, you have 64 kilobit per second. This is how I calculated this. Sampling rate Fs multiplied by R, number of bits per sample, gives you data rate. Gives you this data rate. We call it sometimes RB data rate or DR. DR is equal to Fs multiplied by R, where R is the number of the number of bits representing the quantization level, and Fs is the sampling frequency. Yes. What?
64 kilobit per second.
Yes.
This means consumer.
Yes, consumer, exactly. A computer generates, if you are using your voice and sending voice data, voice signal, then you require 64 kilobit per second. And your DS0 is a hierarchy in your network where it can support up to 64 kilobit per second. So this type of cable can be used for one message signal. Now, there is, after DS0, we have DS1. DS1 is the first level of the hierarchy, that multiplexing process, and it can serve up to, it can carry up to 24 DS0. So what's the data rate of this then? 24 multiplied, approximately 24 multiplied by 64. Because DS0, what's the data rate of DS0? 64 kilobit per second. Then 24 multiplied by 64, you get a roughly estimated like value for the data rate that DS1 supports. The bandwidth of the DS1 is computed from the following equation. So this is what I told you. You have 24 channels because it supports 24. Each channel is quantized with 8 bits. And there is a 1 extra frame for synchronization. And you multiply by the sampling rate, which is 8,000. Then you get the data rate. This is RB, the data rate, which is equal, after all these multiplications, you get that this DS1 can support a data rate of up to 1.544 megabit per second.
What's our frame bit per frame?
1 frame bit per frame, this you need it for synchronization, so that the receiver knows that now this is the starting of my data. I should synchronize to this. They tell each receiver, when you see this bit, this is a synchronization point. You start counting that this is your data. DS2 is the second level multiplexer, and DS2 combines 4 DS1. What this means, each 4 DS1 can be supported by 1 DS2. So what's the approximated data rate that DS2 can support? The data rate of this, which is 1.544 multiplied by 4. The bandwidth of the DS2 is computed from, not the data rate actually. Here, it's like the way I calculated here. He puts 4 here and DS1. But he put also this ratio. Why this ratio is? This is because of the framing, the synchronization thing. And the data rate after synchronization and everything increases from 1.5 to 6.3. So this DS2 is another type of cables or another type of transmission line that can support more data rate. DS3 is the third level multiplexer. DS3 combines 7 DS2 bit stream to obtain a digital signal at rate equal to 44 or almost 45 megabit per second. So you understand the process? The same, you have another type of cable or transmission line called DS4. 4 means fourth level multiplexer. And this multiplexes 6 DS3 and the data rate reaches up to 274 megabit per second. DS5 is fifth level multiplexer, and it's equal to 2 DS4, and the data rate reaches to 260 megabit per second. So basically what you have something like this. This is the summary of these many slides I gave to you. You have DS0, which is this. This is DS0 equal to 64 kilobit per second. Now, 24 DS0, all of them fit into one DS1. That 24 multiplied by 64 gives you approximately this number, after you include the synchronization. Now, 4 DS1 fits into 1 DS2. 4 multiplied by this number give you this. Now 7 DS2 fit into 1 DS3. 7 multiplied by this number gives you this. Now you have DS3. 6 DS3s gives you 1 DS4. So 6 multiplied by this number multiplied by 6, you will get a number close to this. After you include the synchronization, you get the exact number. So this is basically a summary of all the previous slide, the digital hierarchy multiplexers. Clear? Now let's talk about the problems involved in the design of a digital multiplexer. What are the problems? The first problem is synchronization between the transmitter and receiver. It's not always synchronization is difficult, especially in wireless channels. But synchronization, the transmitter and receiver needs to talk to each other so that they agree among them how to do the synchronization. They exchange some training sequences, and they tell each other, when you see these sequences, please synchronize and start taking your data. They do correlation when they have the maximum peak. The maximum peak, this means that the sequences are matching on top of each other, and then you start exactly taking your data bits after that maximum peak. This is basically brief explanation to it, but it's a domain by itself, synchronization. The multiplex signal must include the other disadvantage of this, of the design of digital multiplexer is that the multiplex signal must include some form of framing so that its individual components can be identified at the receiver as well. The multiplexer has to handle small variations in the bit rates of the incoming digital signals. Small variations. For example, you don't always have 20 users, 24 users operating simultaneously. What if you have more? You need to switch directly to another transmission line that can support this. What if you have less? You need to switch to another one so that you utilize your resources efficiently, because at the end it's money, it's bandwidth. Now, this is basically what's digital hierarchy, digital multiplexers, and the data rate that each one supports, and their problems and their challenges. Now let's take an example so that we understand the concept in a more clear way. Let's say we have a speech signal, and this speech signal has a duration of 10 seconds. How can I generate this? I can bring, Audio Lab. There is Photoshop and there is Audio Shop. Yes, Audio Shop is just like Photoshop but for voice. You can change your frequency, make your voice sharper, better. It's very amazing software. I liked it actually. We took it in speech processing course. I used it. Some students, they use it in their analyzing their voice and changing it, modifying it. They making it really amazing. It's something, and you see it. You see your voice signal, and you understand the ups and downs and the silence. Anyway, suppose you recorded your speech for 10 seconds. You have a speech signal like this. The speech signal is usually like this, random. It's not periodic or something. and you recorded for 10 seconds. And this speech signal, it's sampled at the rate of 8 kilohertz. Why 8? Because the maximum bandwidth of your voice signal is 3.4, maximum 4, and then encoded using BCM encoder. The signal to quantization ratio is required to be 40 dB. This is the first given information. You need to highlight these numbers very carefully and map them to their variables and link them to the equations so that you can solve the problem. Calculate, the question says, calculate the minimum storage capacity needed to accommodate this digitized speech signal. That's the question. Now, what would you do? How would you proceed with this question? I would proceed from this equation. Because I know I cannot solve this problem if I don't know the number of bits representing each quantized level. Is it given here? The number of bits representing each, it's not given. There is no R. R is equal number of bits representing each quantized level. Like, is it 4? Is it 8? Is it 7? It's giving me, what's this? This is the duration of the signal. And what's this? This is Fs, which is equal to 2fm or greater. And I know Fs, I know the duration of the signal. I know the signal to noise ratio. But I don't know R. How to find R? This is the first channel. Signal to noise ratio, I know that it's equal to the power to noise. And if you remember from the presentation of finding the BDF of the quantization noise, we were able to derive a formula that links and gives you a direct relationship between the signal to noise ratio and the number of quantized level. What you need to go back to that equation, because I know the signal to noise ratio. From that I can get R. This is the equation that you need to go. This is in the second lecture. You need to go back there and take this equation. And here this is what? 10 log SNR. This SNR in linear or in dB? Linear. This is linear. He's giving me the SNR in dB. You need to convert this to linear and put it here. And then you will have an equation with only one variable, which is R. Then you will be able to solve R, and R we found it to be equal to 7 after you solve the equation. Don't confuse, very important. You know that there is a relationship between the signal to quantization noise ratio. And this is the formula that link them with each other. I gave you this signal to noise ratio in dB. You need to convert it to linear. And then R, you will find R. It becomes simple math equation with one variable. Anybody can solve it. After that, he's asking about the storage capacity. How much memory size I need to store this signal? That's the question about. The number of samples, to solve this, you need to know how many samples you have in this 10 millisecond. How many samples? I know the sampling frequency and I know the duration. I just multiply them with each other. This is the duration of the signal. I take only samples. I don't take all the values of the signal. I take samples. How many samples I have? How would I know? From the sampling frequency, I can take TS. If you know TS, you divide the duration of the whole signal over TS, you get the number of samples you have. Or another way, you multiply the duration with directly with the sampling frequency. How many samples I got? 8 multiply 80,000 samples I have. Within the duration of 10 seconds, I have 80,000 samples at sampling rate equal 8 kilohertz. What's remained then? What's left to complete the question? I need to know each sample, how many bits I require for each sample to represent it. I already found it here, 7. So you multiply this number by 7, you get the data size. This is not data rate, this is the data size. In kilo, for example, in your computer, you say this file is 5 megabyte. This is 6 kilobyte. This signal that you recorded in your laptop and sampled at this frequency requires 560 kilobyte. In other words, almost half mega bit. Yes, if you want to convert this to byte, what do? You divide by 8 because each byte equals 8 bits. Yes? If I ask you, I want the answer, if I am giving you multiple choice and I give the answer in byte, not bit, and the result that you obtained while you are solving the question in bit. So you need to do that trick and divide by 8 because each 1 byte equals to 8 bits. Clear? Another example. So that I give too many examples so that you can understand the topic more and become convenient and familiar with it. A PCM system uses a uniform quantizer followed by a 7-bit binary encoder. Like the previous thing, quantizer followed by 7-bit encoder. The bit rate of the system is equal to, this is the bit rate. This is RB, which is equal to Fs multiplied by R. Isn't that right? I know R, I know RB, I can get Fs. What's the maximum message bandwidth? He's not asking about Fs. Don't get confused. Don't get afraid. Just little by little. Maximum message bandwidth. Message bandwidth, I know, maximum, you are talking about maximum. This Fs, when it's maximum, is equal to 2FM. If I know Fs, if I get and find Fs, I can substitute it here, and from here I can get FM. Isn't that right? And really, this is what I did. Either you solve the question like this, with frequency and data rate, or you solve it with TS and TB. What's TB? TB is equal to 1 over the data rate. TS is equal to 1 over Fs. And R remains R, but changes to the other side like this. This is the other way. And this W is actually FM. So this is the other way of solving it, and you get W max to be this value. Clear?
Yes.
The signal to noise ratio, what do? You already have a direct relationship between R and the signal to noise ratio. These questions are very, very important. Makes you understand things. So it's better to understand them here and also review them at home. What are the virtues, the merits, the advantages and limitations of using PCM? Now, with this lecture, we will end the topic of PCM and we will start with another topic called delta modulation. But before we move on, before we move to another subject, let's understand what motivated us to study this topic and why it's important. Why should someone use digital communication PCM even though it introduces complication in the design of communication system? Yes, why it introduces complication? Because it requires sampling, quantization, encoding, processing, computational power, so many things to do. It actually introduces complication, consumes power due to processing. You need CPU, fast CPU to do this. And due to the complication of computation, You introduces latency, you cause delay to your system, yes? BCM system, in spite of these disadvantages, has many advantages on the other side. Some of these advantages are listed as below. First, it's robust to channel noise. Why it's robust to channel noise? I told you, I showed you one time the signal that I transmit over the channel, and after it moves through the channel, the signal fades. There is some distortion. At the receiver, if I am able to put a threshold here, and this signal is still above that threshold, I can know that this was like this. So I perfectly reconstructed the original signal that was transmitted at the transmitter side. So it's robust against channel noise, while in analog it's really difficult. The second advantage, it has efficient generation of the coded signal along the transmission path. You deal with bits, you group them, you put them on the transmission line, you have multiplexing hierarchy. It's easy. You deal with number actually. Efficient exchange of increased channel bandwidth for improved signal to noise ratio. You exchange your data more conveniently and easily. A uniform format for the transmission of different kinds of baseband signal. Hence, integration with other forms of digital data in a common network is easy, because you have some common line coding formats. Once the transmitter and receiver agree on the format that's used for transmitting your data, then it becomes easy and convenient. Plus, it can be used more easily to secure your signal, because you are dealing with bits, and encryption and decryption actually can be applied only on bit level. It's difficult to apply it to analog signal directly. Comparative ease with which message sources may be dropped or reinserted in time division multiplex system. That's another plus advantage. So these are the key advantages that motivate the use of BCM, in spite of the fact that it introduces computational complexity and latency. This slide summarizes the hierarchy, the digital hierarchy we have, and this is based on North America digital multiplexing hierarchy, which is this slide actually. This also summarizes it. 24 multiplied by DS gives you this, and then 4 of this gives you DS2, 7 of this gives you DS3, 7. This is hierarchy used in America. There is another hierarchy used for Europe, and this hierarchy is, instead of DS, uses E. E1, E2, E3, E4. This is Europe, this is US. Here you have not 23, you have 30. And the data rate becomes 2 mega instead of 1.5. And almost, but like these values are different, yes? You see these differences. Plus the values here are different because it's different standard. And with this, we finish the presentation of the last topic related to BCM.